Okay, so in this chapter, as the title suggests, we'll do applications of Newton's laws. So we'll apply Newton's laws to various situations. Okay. So we'll review what the laws are again. Newton's first law says, well, it is essentially a special case of the second law. This is the second law. The net force acting on an object is equal to mass times the acceleration of the object. And if the acceleration of the object is zero, force is zero. And that's Newton's first law. Okay? So if there's no net force acting on an object, its acceleration will be zero. Acceleration will be zero and velocity will be constant. Okay, so that's Newton's first law. The second law, of course, says what happens when the net force is not zero. When the net force is not zero, you have that acceleration. Okay. Of course, this is the vector equation. So what this means is, mathematically, this vector is equal to that vector. Well, this vector is a scalar times this vector, but this vector is equal to that vector. And what that means is each component, the x component of this is equal to the x component of that. Y component of that is y component of that. Okay. So this is really how many equations? I'm sorry? It depends on how many dimensions you are. If you're in one dimension, that's one equation. If you're in two dimensions, that's two equations. In three dimensions, three equations. In n dimensions, it's n equations. Okay? So there you go. The x component of that vector is equal to the x component of that vector, y component, and so on. Now you also saw this, we talked about this last time. You saw that if you apply a force in the x direction, that's not going to give you acceleration in the y or z direction. Okay? So motion, force applied in the x direction only gives you an acceleration in the x direction. Okay? So for instance, if these were zero and you applied only this force, you would get is that. Yeah. And Newton's third law, of course, says if you apply force on an object, that object applies an equal and opposite force on you. Okay? For every action, there's an equal and opposite reaction. Okay? So for instance, when you drive your car, what propels you? What gives you an acceleration? What is applying the force on you? Okay, so what you do is the tires apply a force on the road in that direction, and the road the tires are trying to rotate and they're applying a force on the road in that direction, and the road is applying a force on you in that direction. So for instance, if it was a frictionless road, if you were on ice, the tires would spin and they wouldn't be able to apply this force, you wouldn't get that force. Yeah. All right, so those are the three laws, and we're going to apply those laws in various situations. Okay, so one of the things you want to become familiar with is free body diagrams. Okay, so for instance, here's a situation that we want to apply Newton's second law. Okay, now what is it that you want in this situation? You're driving down below this and you don't want this falling. You want this guy to be at rest. Okay, well, what are the forces acting on this guy? Here's, let's say, tension 1. Well, okay, we'll say force 1. Okay, so that's a ring, that's one rope, and that's another rope. So that's T1, T2, and the weight of this object. Okay, or we'll write it as force due to gravity. All right, if you want this guy to be at rest, what you want is this to be 0. Okay, the net force acting on it should be equal to 0. You want this guy to be at rest, so you want that to be 0. Okay. So that's what you want. So that's an application of Newton's laws. All right. Now, what a free body diagram is? Okay. So what we're interested in is the motion of this guy. Okay. Well, the motion being you want it to be at rest. So what a free body diagram does, okay, just draws the essential things. Okay, so here is a free body diagram of this situation. Okay. So this object is represented as a point. Okay. And for now, that's what we're going to do. No matter what it is, we're going to represent it as a point. Okay. We will start representing things as not points when we start talking about objects spinning. Okay. So that won't happen till, let's say, chapter 10 or so. Okay. So right now, as long as it's only linear motion, we'll represent them as point objects. Okay. Yep.
What about the third law?
I'm sorry?
What about the third law?
Action and reaction are equal and opposite.
Like, what is the principle? Third law, like F equals to?
There's no equation. No. All it's saying is this object applied a force on the wall like that, and the wall applied a equal and opposite force. And that applies in all situations. So for instance, let's say the earth is pulling me down with a force of 160 pounds. And I'm pulling the earth with a force of 160 pounds. Okay. Okay, so in a free body diagram, we just draw the essential things. Okay, so here's our object that we're considering. And these are the forces acting on the object. And if this object is at rest, then the sum of those forces must be 0. And if that object is accelerating, then the sum of those forces must equal the mass times the acceleration of that object. Okay. So here is our object. Okay. There's tension 1, tension 2, and the weight. Okay. And if it's at rest, see, there's the y component of the tension, x component of the tension. This must cancel that, and the sum of these two must cancel that, which we did in one of the previous problems. Okay. So here was a case where you wanted the acceleration to be 0. Here's a case where the acceleration is not 0. So here's our object. Okay. Here's a force being applied by this tugboat. Here's a force being applied by this boat. And this barge is accelerating in that direction. So there's the barge is represented by a point object. Okay. This force is applied like that. This force is applied, there's that force on that point object. What is this guy? I'm sorry?
Drag.
Yep. Where is the drag coming from?
The motion.
Yeah, so there's the drag force. So there are these three forces acting on him. And the sum of these three forces is not 0. Why is it not 0? I'm sorry?
It's moving.
Well, it can move. And it is accelerating. Very good, my friend. It can be moving, and this net force can still be 0. Okay. All right. So it is accelerating. Now, this is something that you learn in chapter 10. Okay. This kind of stuff is true as long as these forces are acting through the center of mass of the object. Okay, I haven't told you what all that is, but you guys intuitively know this. So for instance, if this barge was pushing over there, what would happen?
Rotate.
It would rotate. Okay, so we don't want to account for all of that. Okay, we don't want to complicate things. Okay, so right now, without having said so, all the forces are acting through the center of mass of the object. Okay? All right, so anyway, this is the free body diagram. We want to keep things very simple. And now we'll apply Newton's second law to this object. If this guy is accelerating, then the sum of these forces is equal to mass times acceleration. Okay? Now, the free body diagram we apply to whatever object it is that's moving. Okay, so here's the situation. So let's say here's an elevator. So let's say the elevator is accelerating in that direction. Okay, so you could consider the motion of the person. You can consider the motion of the whole elevator, whatever it is that you want to consider. Okay, or if it's moving at constant velocity, what is the acceleration then? 0. Okay. What is the acceleration of the elevator? 0. What is the acceleration of the man? 0. Okay. So let's say if you want to do the elevator, okay, the free body diagram would be, okay, again, what are we going to write the elevator as? A point object. Okay. What are the forces on the elevator? There's this object cable attached to the elevator, so that's applying a tension T. What other force is acting on the elevator? Gravity. Okay? The weight of the whole thing. Okay? mg. Okay? Let's do a free body diagram for the person. What are we going to write the person as? A point object. What are the forces on the person?
1G either way.
So let me, capital M is the mass of the elevator. Okay. So now for the person, gravity never quits.
The forces that
I'm sorry?
person exudes when you're standing to not like sink into the floor. So like the counter force.
Yes, so and that's got a name. That's the normal force. Okay. Okay. So see, the guy is standing on the spring balance, and the spring balance is exerting a normal force. And there's the force of the spring balance. Those are the only two forces acting on the guy. Okay. And if he's not accelerating, then those two must add up to 0. And if he's accelerating upwards, that must mean that this force is greater than that. And if he's accelerating downwards, that means this force is greater than that. All right. So let's look at this. Okay, so for the person, we'll write with this axis being positive, mg minus the spring force equal to mass times acceleration. Okay. So let's say the elevator is accelerating downwards. Okay. All right. So what if this is g? If the acceleration downward is g, what is fs? If this is g, mg will equal this. This would be 0. Okay. Fs equal to 0. That's weightlessness. So you want to experience weightlessness, go in an elevator, cut the cable, and you'll experience weightlessness for a few minutes, a few seconds. All right, so here's another point that we want you to be aware of about free body diagrams. Okay, again, you already saw this here. Okay, you can apply Newton's laws to any object. So you wanted to consider the motion of the whole elevator, you apply the forces to the whole elevator. You wanted to consider the motion of the person, you apply the forces, Newton's laws to that person. Okay. So similarly, here's multiple objects. So here are two objects attached via the string. And okay, so right now we'll consider where the tension is the same. Okay. Tension in the strings are the same. Again, do you guys remember when the tension is the same, what is assumed? I'm sorry?
The pulley is, I don't know what it's called.
Right, the pulley is massless and frictionless. Okay. Okay. All right, so we'll apply Newton's laws to this guy. Okay. So let's draw the free body diagram for this guy. There's this tension acting in this direction. There's the weight, and there's the normal force exerted by the table. So there are these three forces acting on this guy. And then you can look at the motion of this guy. There are only two forces acting on this guy, the tension and the weight. Tension and the weight. Okay. And so you would, so this is the free body diagram for that guy, and this is the free body diagram for this guy. Okay. Okay, so here's another object machine with multiple objects. Okay, and we'll actually use this. We'll do an experiment with one of these devices. Okay, and Mr. Atwood invented this machine for the following reason. So he wanted to measure the acceleration due to gravity. Okay, and back in those days, this thing, well, so with the timing devices they had, this thing fell too fast. It's still falling at the same rate, except that our timing devices have gotten better. Okay, so it's easier to measure G. So you had to slow this fall down somehow. And this is the device he invented. Okay, so with the counterweight, you can slow down its acceleration. Okay, so you can make this acceleration, given this counterweight, you can make this acceleration anything you want from G to 0. Okay. I'm sorry?
I think the heavier mass increase that, like M2 increase from M1.
Mhm.
Give you the answer. M2 minus M1.
So depending on, okay, so if M1 equal to M2, then acceleration will be 0.
No, I don't mean equal.
Yeah,
I mean, one of them should be
less. Yeah, one of them is heavier. Yeah.
the heavier
Object. Yeah.
the heavier minus the.
Right. Yeah, we'll derive that. Yeah, we'll derive that. I know what you're talking about. So just give me 1 second. Okay, but this device is to make, you can have any acceleration between 0 and G. Okay, and so here's what you're referring to. So for now we'll say okay, so the free body diagram for this, okay, so again, tension is the same, implying this is massless and frictionless, even though that looks like a very big pulley, and so it, okay. So there's M2G minus tension, so let's write M2G minus tension equal to M2 times A. Okay. And this guy is accelerating with the same acceleration in that direction, right? T minus M1G equal to M1 times A. Right? Now we'll add the two equations. This will cancel. M2 minus M1G equal to M1 plus M2A. Okay. And this is what you were referring to. Yeah. Okay, so what this equation is telling you is this system is acting like its total mass is that, and the net force on it is the difference in the weight of this object. If the difference in the weight of the object is 0, the net force acting on it is 0, and its acceleration would be 0. All right, anyway, let's look at this expression. Okay, so, and let me write it like so. I know this will appear odd, but I'll write it like that. Okay, so you guys understand, if M1 is 0, if this guy will have a free fall, and his acceleration will be g. So when M1 is 0, A will be equal to g. Okay. So when M1 is 0, A will be equal to g. Okay. And when M1 is equal to M2, this is 0, and A will be 0. All right, so you can have a value of A anywhere from G to 0, okay, as the mass of M1 0 to M2. So as the mass of M1 changes, okay, this would be G, this would be 0. Okay, so you can dial it any way you want as you go from here to there. You can choose whatever acceleration it is that you want. Okay, and that was the idea of this guy. All right. Okay, now we'll talk about friction forces. Okay. Without friction, you couldn't walk. Without friction, you couldn't drive, and so on. Okay. So friction is useful in many situations. In other situations, it's not so useful. Okay. Friction is the force that arises when two solid objects try to move relative to each other, that are in contact with each other. Okay, so if here's a box sitting on the floor, if you try to move it in this direction, the friction force will be in that direction, and friction forces are denoted by little f, okay? And the same object, if you move in this direction, the friction force. So the friction force is always in the direction opposite to the direction of motion. It'll depend on what two types of surfaces are in contact, okay? And it turns out that it's independent of the area of contact. Okay. It's independent of the velocity. So this force depends on the two types of surfaces that are in contact, and it depends on the normal force. Well, the normal force is related to how hard this guy is pressing down on that. Okay? So if it's just the weight, then the normal force is equal to the weight. But you could be pushing on him, so the normal force would increase. Okay, so for instance, right now there was a friction force on that. If I push down and now you try to move it, the friction force is greater. You guys understand that? Okay. Yep.
The mass increase, the friction will be increased, and even depends on the surface. If it's like soft.
Yeah, it depends on the surface and the weight. Yep. So you can take a block of rubber and put it on this table, and if you double the mass of the rubber block, then the friction force doubles.
It's different than in the floor.
Yeah, it depends on the surface. For the same surface, it depends on the normal force.
Is that why mg cosine will matter?
That's when yeah, okay. Very good. So it will depend on the normal force. Okay, so let's okay, so between two solid surfaces, it's called a friction force. when you fall in a fluid, air is the fluid is exerting a friction force. So if you're falling in this direction, the friction force will be in that direction. If you're going in that direction, the friction force will be in that direction. The fluid friction force exerted by the fluid is called a drag force, and we give it, I guess, so that's it. We give it a special name. Okay. Now let me show you an app before we get into the slides. All right, so okay, so you guys see in this guy's pushing, there's the applied force, and the object didn't move. Why didn't the object move? Because there was a friction force in that direction. Okay, and this is called a static friction force because this the object is not moving, and that's why it's called a static friction force. So how's that friction force being applied? How is that friction force being applied? Okay, so here's a rough model of it. Okay, so you can think of it, so here are the two surfaces, and the molecules of these guys are forming a loose bond with the molecules of that guy. This guy is trying to move to the right, and those molecules are pulling back with that force, and they're preventing him from moving. Okay. Now here's the deal with the friction force. Okay, so I'm going to go back to that application. I apply a 10 Newton force, and this guy didn't move, so all those forces add up to 10 newtons. Okay, let's apply a 20 Newton force, and the guy still didn't move, so these guys applied a 20 Newton force. Okay, so those bonds got stronger. Yeah, so the net force is 0. So the point is, this static friction force, denoted by static friction force, can be anything from 0 to a maximum value. Okay, do you guys understand? When I apply this 0 force, the static friction force is 0. Okay, there is a maximum force I can apply. There's a force I can apply. So the minimum force that I can apply to get it to move is the maximum static friction force. Okay, all these bonds can only pull so hard. If you apply with a force greater than the maximum force they can apply, that'll start moving. You guys understand? All right, so again, let's go to that. Okay, so I've applied a force 96 newtons. You guys see this, 96 newtons, and watch that number. Okay. 110 newtons, so the static friction force, 120 newtons, it's still not moving. Okay, it started moving. So the maximum static friction force is somewhere between 120 and 129 newtons. Okay. Okay, 124 newtons, it's not moving. 127 newtons, it's moving. Okay, so it turns out in that simulation the maximum static friction force was 125 newtons. Okay, all right. So the friction force depends on the surfaces in contact and how hard they're being pushed against each other. It's independent of the area of contact. Part of the friction force is because of the roughness of the surfaces in contact. However, much of the friction force is due to the attractive forces between molecules of the two objects. Okay, is due to the between molecules. In fact, perfectly smooth surfaces of similar material would adhere to each other, forming a cold bond. Okay, and they always act in a direction opposite to the direction of motion. Okay. Two rough surfaces in contact have a much smaller area of actual contact than the total area. So this might be the total area of contact, but if you add up only the actual area of contact, that's of the order of 1 part in 10 to the 4 in 10,000. So it's like if you point a pencil on a piece of paper, the dot you make, that's the area of contact. Okay, the actual area of contact. All right, so here's our object. We have applied this force. There's the static friction force. Okay, what does that mean? This guy is still at rest. Okay, so in this graph, what this is showing you is this is the applied force, and that's the static friction force. So the object is not moving. This is the maximum static friction force you can have between these two surfaces. Okay, so you have to apply a force greater than that to get the object moving. Okay, so when this applied force is greater than that, this object will start moving. Okay, and once this starts moving, the friction force is now kinetic friction force. Okay, it's called kinetic because now the object is moving. And this guy is always smaller than the maximum static friction force. That's what we find. Okay, the kinetic friction force is always smaller than S max. Okay, so there is the maximum static friction force, and once you start moving, there is the kinetic friction force. Okay. And the kinetic friction force is given by mu k. This is called the coefficient of kinetic friction times the normal force. Okay, in this diagram, there's the normal force. Okay, so this force, the kinetic friction force, is equal to mu k times the normal force. Mu k depends on what two surfaces are in contact, and that tells you the stickiness of the surfaces. Okay, so that's a measure of the stickiness of the surfaces. What are the dimensions of this guy? What are the dimensions? What is this? Force. It's newtons. What is this? Force. So this is a dimensionless quantity. Okay, so this is a dimensionless quantity, and what are the values it can take? It can be anything from 0 to infinity. 0 would be a frictionless surface, and of course infinity would be superglue. Okay. Okay, so the maximum value of the static friction force is mu s times Fn. So Fn S maximum is mu s times the normal force, and the kinetic friction force is always mu k times Fn. Since the maximum static friction force is always greater than that, that means this is always greater than that. The static coefficient of friction is always greater than the kinetic coefficient of friction. Okay? In very rare cases can it come very close together. Okay? Okay, again, these guys are called coefficient of, well, let's see, I don't need to, yeah, so those guys are called coefficients of friction, mu k, that measure the stickiness. Okay. Now these numbers are important enough where they give you tables for various materials. So rubber on dry concrete is mu s is 1. Rubber on wet, so mu s is 1, and mu k is 0.8. Okay. So now you guys don't know this, but in the old days, you try and get car insurance and they would ask you if you had anti-lock braking systems. Now that's standard feature. Okay. You know about it?
Anti,
Uh,
sorry. not
ABS.
very well. Yes.
Yeah.
Fraction,
What's that?
fraction control.
Yeah. Well, also, so what that is if you lock your brakes, then the car starts sliding, and then you're using this kinetic friction, and so the friction is smaller, and you take longer distance to stop. Okay. If you keep rolling, if the car keeps rolling, what you're doing is if it's rolling, that means the car is not slipping, and you're using this friction, static friction force, and you're stopping faster. Okay. Professional drivers can pump their brake and stop. They don't need anti-locking braking system. Yeah. Guys like me need anti-locking braking system. Yeah. All right, so but nowadays it's standard feature. Okay, so these are important numbers, and they give you these numbers. Okay. Let me give you a meaning to this number, for instance, and then you'll figure out what all these numbers mean. Okay. So what we're going to do is we're going to try and understand this number, 0.8. Okay. So we are going to put a 100-pound rubber block on dry concrete. Okay, so that's the weight. So the normal force is 100 pounds. Okay, and the kinetic friction force is mu k times the normal force. It's 0.8 times 100 pounds, 80 pounds. So the kinetic friction force is 80 pounds. So if you want to move this block at a constant velocity, if you want to push it from here to Palm Coast, you have to apply a force of 80 pounds. So that's what that number means. Okay? So you have to apply a force of 80% the weight of the object to move it at constant velocity on a horizontal surface. Okay? All right, so here's a free body diagram for skiing downhill. So here's the skier. Okay, there's the component of the weight. This is mg sine theta. There's friction force. Now that we've learned about friction, we're going to account for friction. There's the friction force. There's mg cosine theta. And there's the normal force. So this is mg sine theta, mg cosine theta. There's the normal force. And since you're not coming off the slope, the normal force is mg cosine theta. Okay? And so the friction force is mu k. So mu k is mu k for the skis and the snow, okay, times mg cosine theta. Okay. And what is the acceleration of the guy down slope? It's mg sine theta mg sine theta is the component of the force of the weight in that direction, minus fk equal to mass times acceleration. Mg sine theta minus mu k times mg cosine theta, mass times acceleration. Okay, so you will solve problems like this. You'll see this. Okay. The acceleration of this guy down the slope is this force minus this force. Okay. That force minus that force. Now this kind of stuff is important. This stuff happens in real life. You can Google it and see how many fatalities there are in truck drivers. Okay, so let's say here's a truck carrying a heavy load, and so this is okay. So this, let's say this truck is going on a highway fairly fast, and then a wall suddenly jumps in front of the truck. Okay, now for the truck driver, this wall is a problem. Okay, so the wall stops the truck driver fairly fast. That's a problem. Again, you don't want large accelerations. Okay, so that was the acceleration of the truck. What was the acceleration of this guy? Same thing. What is giving that guy the acceleration? Static friction force. But the static friction force has a maximum value. So if this force can't give you that acceleration, this guy goes and crushes it. It's a double whammy. This is a real problem. That's why these things, all heavy loads, are chained down and stuff. Okay. So, did you guys understand that? So anytime you see a heavy load, you'll see it's always chained down. Now there's a lot of construction going on, and on the highway you'll see a lot of trucks carrying these cinder blocks for buildings and stuff like that. They're always chained down. Okay. All right. So this thing is, so I'm going to give you a top view. Okay, so here's our car driving around in a circle, and to keep things simple, we'll say it's going at constant speed. Is it accelerating? Yeah. Why is it accelerating? Yep. So, and the acceleration of the car is in this direction. It's called centripetal acceleration because the acceleration is pointing towards the center of the circle. So here's okay. The force of gravity is directly downward. What is giving the car an force in this direction? You need a force in that direction. What is providing the centripetal force?
Frictional.
I'm sorry?
The frictional.
What kind of friction? So it's a static friction force. See, the tire is not moving in this direction. So it's a static friction force that's providing that. How do friction forces come about? Because those molecules are bonding, the tire molecules are bonding to the road molecules. Okay? So if you're relying on static friction force, you're leaving rubber on the road. And that rubber costs the country billions of dollars.
So every time the tire rolls,
Mhm.
there's rubber molecules sticking to the ground.
That's right. Why do you think your tires wear out? If there weren't rubber molecules, right? So they give you $40,000 miles worth of rubber on your tires.
So they bond that quickly.
Yeah.
So what about
Mm?
what about other materials in motion?
Wood.
I mean, I know it doesn't just happen to rubber, but
Mm-hmm.
if you slid something across a table,
Mhm.
would it even to some scale do the same thing?
Yeah, okay, so when do you leave it? When the bonding is comparable to the intermolecular bonds themselves. If the intermolecular bonds are if they're holding on to each other with a force of 100 pounds and the bond with the table is 10 pounds, then you won't leave much.
Okay.
Okay, that's what happens in metals. You slide a metal, yeah. Yeah. Mm-hmm.
Does the temperature affect how much would stick to the surface?
Yep. How do we know that? So, you guys have watched drag racing. They warm the tires first. Okay. So when the rubber is warmer, it holds on harder, and you can accelerate faster. Yeah. Okay. So this is a static friction force, and again, so how do we fix that problem? You bank the road. Okay. Now let's see what happens. Okay. You guys understanding this? Okay. So the curve, the center of the curve is in this direction. You need a centripetal force. Okay. How much centripetal force do you need? What was the centripetal acceleration? It was v squared by r. Remember, v was your speed. Okay. That's how much you needed. So equal to mv squared by r. Okay. So what you're going to do is you're going to bank the road. There's your weight. The road is pushing you with that force. Okay. That force is balancing, okay, so balancing mg cosine theta. No. So this component of the normal force, okay, so F and sine theta is providing you the centripetal force. Okay. So N sine theta is providing you the centripetal force, and the cosine theta, N cosine theta, this force is balancing the weight of the object. Okay. So by banking the road, this component of the normal force provides the centripetal force, and this component of the normal force is balancing the weight. Okay. So now if you take this, if you divide this equation by that, tan theta equal to v square by gr. Okay. So if you drive at this speed on a road that's banked, the normal force will provide you the centripetal force. You don't need any friction. If you drive faster, then you'll need a static friction force. Okay. Then a static friction force will have to come into play to provide you additional centripetal force.
Is that why the highway exits have a speed limit?
So the highway exits all have a speed marked. It's not a speed limit. If you go at this speed, you won't come off. You don't need static friction force. It can be as icy as it wants. You won't slip. So you have to drive at precisely that speed. If you drive at less speed than that, you'll slide downward. If you drive faster, you'll slide upward. Okay. So the speed corresponding to the bank on the International Speedway, on the curve, it's 90 miles an hour. So it snowed. If the road got icy, you'd have to drive at 90 miles an hour not to slip down. Okay. Now, there's something that's very beautiful about this equation. Can you tell me what's beautiful about this equation? And you've all experienced this without realizing it. It doesn't depend on the mass. It doesn't matter what you're driving. That bank is the same. The speed is the same for all objects. Yep. Go ahead.
So sometimes the mass is a good thing, sometimes it's a bad thing. So
Mhm.
My question is, so if we don't have like enough mass,
Mhm.
so that's will lead us to lose the control of the ABS because we don't have a weight to hold us on the
Mhm.
street, so there is no traction, like good traction.
Mhm.
But we need like mass until a limit. But if we go over, it
Mhm.
will be a problem because the mass will push us in the front more.
Mhm.
So is it true or that the mass can be a good thing and the same thing can be a bad?
Well, if you're trying to go fast, then mass is always a bad thing, right? Is right? Um, so you're still talking about curves. Are you still talking about making turns?
No, I'm talking about mass,
Mm-hmm.
which is if it's increased,
Mm-hmm.
that will help us if we are in a low speed to stop quick. But if we are in a like high speed and the mass is increasing,
Mm-hmm.
that will let us lose the control of it for the car. So even if you try to stop the car will.
Well, if your mass is high, you need a much greater force to stop. So, for instance, it's harder to stop a truck than a car.
That's what I mean.
Yeah. Yep. Okay.
Does this kind of work in tandem with, like, I think it's Bernoulli's experiment where, like, he dropped the ball on the curb and he found it took the same amount of time to get to the bottom, no matter where he dropped it, in the calculus?
No, yeah, that is that tautochrome problem. We'll come to that. Yeah. No, so that's just a special curve.
Oh.
Yeah. That's an inverted cycloid, but we'll get to it. Yeah. Yeah. So is that a homework problem in your calculus class? That's a very
it was.
interesting problem. Huh?
Yeah, that's a good problem.
Yep, it's a very good problem. Yeah. All right, so this is a device to save billions of dollars for the country. Okay, so you don't have to rely on static friction, and it's also a safety feature. So if you're driving up north in the winter, if you drive at that marked speed, then you don't have to. Okay, so again, here's the lift force. So if you want to, you can't turn a plane without banking. Okay, so it's this component of the lift that provides you the centripetal force. Okay, so you can't turn a plane if you're flying horizontal. Okay, you have to bank it. Okay, and so for a given speed, the greater the bank angle, the smaller the radius. Okay. All right. All right, now we'll talk about drag forces. Do you guys have the patience for me to finish this? Otherwise, I'll have to start a new recording. Okay, let me finish this and then we'll start lab. Okay. Now we'll talk about drag forces. These are friction forces when you move in a fluid. Okay. So it turns out that these, so for instance, if an object falls in a fluid, if you're in a fluid, you'll experience, so this is velocity, you'll experience drag forces. Now this drag force is a function of your velocity. Okay. So it turns out that the magnitude of resistive force when a body moves in a fluid depends on the speed in a complex way. We consider objects moving in air. Of course, the Navy also is interested in objects moving in water and stuff like that. So the drag forces in a liquid are much greater than in air. Okay. For small objects falling slowly, such as dust particles falling in air, the resistive force is proportional to the speed. So for small objects falling in air, the drag force is proportional to speed. Okay. And now this sort of stuff is important. So for instance, the wind blows and it blows up a lot of dust and pollen and all in the air. If you are allergy sufferers, you want that dust and all that to settle down fast. Okay. For larger objects such as skydivers and cars, the drag force is proportional to the square of the speed. Okay, the drag force is proportional to the square of the speed. Okay. So let's say you jump off a plane. When you jump off the plane, first your velocity is 0, so the only force acting on you is gravity. Okay. And then as you gain speed, now the drag force is non-zero. Okay. So you will keep gaining speed as long as this guy is greater than that guy. But this guy is increasing with speed. So eventually you'll reach a speed when this guy is equal to that guy. Right? See, this guy is not changing. This guy was 0 to begin with, and then he's starting to increase because your speed is increasing. And the maximum value he can increase to is mg, if you're not wearing a rocket and diving. Okay? And then you have reached terminal velocity. Okay. So anyway, so this drag force, so when you jump off a plane, this drag force, here's the formula. It's 1/2 times the drag coefficient. Drag coefficient depends on your shape and stuff like that. Okay, and it's a number. It's a dimensionless number between 0.5 and 2. So for instance, for a Tesla, it's closer to 0.5. For a UPS truck, it's closer to 2. Okay. Rho is the density of the fluid you're traveling in air. So A is the area of cross section. Okay, so if this is an object and you're traveling in this direction, A is this area of cross section. Okay. And V is your speed squared. Okay, so there's the formula for the drag. Okay, so for this cat falling down, there was the force of gravity, and the drag force now is equal to that, and the cat has reached terminal velocity. So when you reach terminal velocity, the drag force minus the weight is 0. And so the terminal velocity can be calculated for objects. Okay. And this thing is good in many situations. So for instance, raindrops reach terminal velocities of 9 meters per second. So for instance, raindrops are falling from clouds that can be 3, 4, 5 kilometers up. And if there were no drag forces, that would be bullets raining down. You couldn't walk in the rain. Okay, so that's a good thing if you want to walk in the rain. Okay. If it rained down golf balls, they would be traveling at 100 miles an hour. You don't want to be walking in golf. Okay. See, hailstone, they're bigger, and they reach a terminal velocity of 14 meters per second square. 14 meters, that's about 35 miles an hour. And they can put dents in your car. Okay. All right. Now, till now we were falling in air. Now, if you fall in liquids, okay, so the quadratic dependence of air drag upon velocity does not hold if the object is very small, is going very slow, or is in a denser medium than air. Okay, so the drag force when you're falling, if you drop something or if something is traveling underwater, the drag force is proportional to velocity. Then we find that the drag is proportional just to the velocity, and this is given by Stokes' law. Okay, so eta, this is eta, that's the viscosity of the fluid. Viscosity is a measure of the friction in the fluid. R is the radius of the particle. V is the velocity of the particle, and Fd is the drag force. Okay. So here's an object that's falling in a liquid, let's say there's the drag force, there's the force of gravity. Okay. Coriolis force is a fictitious force. This is a fictitious force. It's not a real force. You perceive this force because you're in a non-inertial frame of reference. Okay, I'll quickly tell you. So in the northern hemisphere, the counterclockwise rotation around a low pressure center, and around a high pressure center you get a clockwise rotation. Okay, so here's how this thing arises. Okay, so here's the Earth, here's the equator. Okay, how long does the Earth take to go around once?
365.
24 days. I mean 24 hours. Okay. The radius of the Earth is 4,000 miles. Okay, so the circumference of the Earth is 2 pi r. That's about 6 times 4, roughly 24,000 miles. So if you're at the equator, you're traveling at 1,000 miles an hour. Okay. What if you're Santa Claus? How fast are you traveling? 0 miles an hour. Okay. If you're here at this latitude, you're going in a smaller circle. Your speed is less than 1,000 miles an hour. Okay, so we'll make it at, let's say, we'll call it 700 miles per hour. Okay, so let's say we are in the equator. This air is traveling at 1,000 miles an hour. If we were doing this in New York the air is traveling at 700 miles an hour. Okay, so now let's do another diagram. Okay, so now let's say, so this guy was traveling at 700 miles an hour. The ground here is traveling at 800 miles an hour. Okay, so let's say this packet of air starts blowing this way because there's a high pressure and a low pressure here. This block of air only had a 700 miles per hour velocity in that direction, and the ground here is moving at 800 miles an hour, so this guy will fall back. This guy will just move in that direction. If this block of air were traveling toward this low pressure, this guy was traveling at 1,000 miles an hour, and the ground is only traveling at 800 miles an hour, so this guy will go ahead. Okay? And because you're observing from standing on the Earth, which is a non-inertial frame, it appears that you have a force that's deflecting this air. There's not a force. It's a ground that is moving faster or slower relative to your air. Okay, and so you around a low pressure you see a counterclockwise rotation. Okay, and that's what's happening here. Okay. All right. Now biology understands physics very well. Okay, so you have seen geese flying in formation like that. Why do they fly in formation like that? I'm sorry? To reduce drag. So the goal is, if you were a geese flying by yourself from point A to B, let's say if it takes you 1,000,000 joules of energy to get from here to there, if you fly in formation, maybe it might only take 900,000 joules. I'm just making up the number. I'm sorry?
The Air Force.
So, okay, so if you're flying in formation, okay, so here's the deal. So you have a net saving of energy. Well, when you're flying like this guy's feeling the greatest drag. These guys are feeling less drag. Why would this guy do this? He'd end up spending more energy than that. No. They take turns.
Yeah, I was about to say that.
Right.
I'm sure they take turns. They
Right.
can stop and rest.
No, so this guy will lead for a while, and then he'll go back. I guess so. They all take turns. So by flowing information, you save energy. Okay? All right, guys. That ends this chapter. I hope you learned something.